test and maintain the circuit functionality. Okay, so a position of what we say a scan testing we have seen, where scan path testing was there when we interlink all the flip-flops from one stage to the other in a chain fashion. That is scan path testing. And here the boundary scan cell yesterday we have stopped, wherein the boundary scan cell will be comprising of plenty number of repeated boundary scan cells which are communicating between the core logic as well as the external pins. Okay, so these are the pins available for the end user, we are saying. So external pins or towards the core logic, whatever the communication that can happen is through boundary scan cell. Okay, now the control of this data movement, or what you say, the sequence appearing or the system response monitoring, all this will be controlled by the tap controller. And how this boundary scan, each boundary scan, if you take each boundary scan cell, what is that actually um, the setup which will be taking the data either to the external pins or as a scan chain, or between the core logic and the external environment. Maybe if we can see the integral structure, each boundary scan cell if one cell we take, how it will be is either it should be the input or output, or the what you say, maybe we can specify this as parallel input, this is parallel output, serial output, serial input. Like this you can refer back here. Each cell, if you are taking, we are describing something like, sorry, we are taking 4 paths. No? This is 1, 2, 3, and 4, and this is our boundary scan set. Okay, so something like if from this point it is taken as the input, maybe this is parallel in, parallel out, and this is serial in, serial out. Okay, and something like this parallel operation is, see, when the boundary scan is towards the left side, it is taking from the parallel input, giving to the core logic. If it is towards the right side,
Ma'am,
it is, yeah,
ma'am, can you record the meeting, ma'am?
recording, yeah. So when this is towards the right side, the input will be from core logic, output will be that this is parallel out. Okay, and when you're taking the data for testing and all, this is serial data, this is serial path. So serial in, serial out. So parallel in, so this parallel in, if you can specify the path, maybe this parallel input can be, say, if you are taking towards the right side, it can be from core logic. If this boundary scan is towards left side, or it can be from the, what you say, input pin. Okay, so 2 ways, like the input can happen either from the external pin or from the core logic. So parallel out, if you take towards your left side, if your core boundary scan cell is there, this parallel out can be what you say, to the core logic. The output can be given to the core logic from this side. Okay, if that is towards the left right side, it can be the output pin given out to the output pin. Okay, so this is parallel in, parallel out. And serial in, serial out is that something like this. If this is input, if this input can be the test data input or serial data input, scan data input. Both means the same. Both means the same. According to the textbook or the author, they name it as the test data input or the scan data input. Both means the same. Okay, this is the pattern of the input that will be applied for testing the circuit. Okay, or if this is not taken from the external pin, this input can be from what you say, no, not from, because this is input. No, this input will be given to next cell or what you say, boundary scan cell in specific. Okay, because this is kept in this format, each boundary scan cell. Okay, and this one, oh, sorry. This one, this is not the next cell. Let me see. This is from tap controller, okay, or else from previous cell. Because if you have one more cell, which is boundary scan, this can be from previous cell. If you take in this series, serial output means it can be to next boundary scan cell, or what you say, if this is the final element, say, if this is test data out, or this you can take it as test data in, or test data out. So these are the things that each boundary scan cell should be having. Okay, or one boundary scan cell repeated for plenty number of times, because the structure won't change, only the signals that are getting connected will be changing according to the placement of the boundary scan cell. Okay, here this typical boundary scan structure, if you can see, it will be using muxes and D flip-flops. Two muxes and two D flip-flops in order to have these four paths. Okay, so the first mux will be placed, and this is the pair of D flip-flops and next mux. Okay, this is the placing. Now let us write the paths. Now writing the path, we need to represent this data, that is the parallel data. So this will be having, say, if this is 0 and this is 1, either a load or shift will be the control. Maybe if you are taking the 0, it will be load. If it is 1, it will be shifting. Okay. And two inputs. First input will be the parallel input. As we said, parallel input is from core logic or the input pins. Okay, this is, say, scan data in or test data in. Okay, and this is the parallel operation. This is serial input. This is parallel. Okay, the same parallel, like if it is parallel operation, it will be directly moving to the parallel out based on your what you say, the path you are choosing. Say this is 0, this is 1. This is if it is a normal operation. Something like normal operation means directly input is given, your core logic will be given some sufficient time to evaluate the output, and you will be getting the output directly. So if that is a normal operation, if you are testing means through all the boundary scan cells, the data has to be processed, and what you say, according to the status available, the core logic will be evaluating the outputs with respect to the status and the inputs that are applied continuously. Okay. So this is either a normal operation or a testing operation. Okay. If it is a normal operation, parallel into, parallel out. Okay. If not, if it is a shifting of the data, means this is testing operation, the testing mode. First D flip-flop will be enabled, like enabling chip enable will be given independently for each flip-flop. So chip enable, something like this is a capturing of the scan data in or shifting the data based on the logic. And obviously these two should be working on the same clock. Okay, so this becomes the, what you say, test clock. From the tap controller, it will be taking. So this chip enable, this chip enable will be given a signal. If it is enabled, means this will update the output of the first flip-flop to the next stage. So updation. So maybe if you say first flip-flop and second flip-flop, this will be your input to the networks. Now, what are the things we were having in this is parallel in, parallel out we have given. Okay, and we need to take the serial operation. So serial operation is that something like this is serial in and serial out will be here. This point is your test data output or the serial output point. Okay, that means this can be to the next boundary scan cell or boundary scan register. Okay, so what is that it is doing is, this is trying to capture the what you say, the data that you are giving either parallelly or serially. So this is the flip-flop used for capture operation, and this D flip-flop is just to update what is being captured there, update operation. Anyhow, here we have given, when this is enabled, it updates the information either given serially or parallelly. Okay, so like this is your internal structure of the boundary scan cell. Internal structure of the boundary scan cell. Okay, so it is the typical structure what we have given here. Let me give in a registry format. Maybe if you can understand the architecture format, the boundary scan architecture. Something like if we take multiple number of registers, like such type of registers, okay, like we call them as boundary scan register setup, like this is one, and boundary scan register 2, because two registers we are using, and a bypass path is this one. This path is bypass path. Okay, this is boundary scan register 1 and register 2. Okay. And your tap controller will be giving you the instruction of what should be the instruction where it has to be taking to, whether it is the test data that has to be loaded or the system response that has to be loaded. So the architecture wise, if you can see, we can visualize this as the set of two boundary scan registers and one bypass path. I can write this something like boundary scan register 1, boundary scan register 2, and this is bypass. Okay. Now, so these registers will be getting the data either from the test path. That is, your test path is nothing but your test data input or scan data input. Okay. This will be if you are taking the, what you say, testing. If not, directly you can bypass this. Okay. So this is either from your input pins or from core logic can take, which captures and updates. This is your update register. And this updation, okay, after updation, what is the output you get here is when you tap here, this will be two output pins or core logic. Okay. Like if this is the setup of towards the left side, this goes to core logic. If this is towards the right side, that data will be going to the output pins. Okay. So using this, either bypass or through the registry setup, this is equivalent to the previous circuit what we have given there. So this is mux 1 say. Okay. This mux 1 will be giving the data if it is direct. So I can have a tap controller and instruction decode register setup, which will be giving the instructions to this mux, either to update or capture. Okay. And this, based on the instruction that will be given, say if I take this as one controlling segment, one segment of control, see here, this will be controlled or issued by the instruction decoder, whatever the instruction that decoder decodes and gives that to the setup of the registers. Now, once you complete the iteration, you need to have the next instruction address. So instruction shift register will be giving you the next iteration that has to be performed. The same instruction will be given to as the mux, and this will be to what you say output of what is the final output. That means when if this is at the final stage, it will be test data output or scan data output. If it is not at the final stage, it goes to next boundary scan set. Two parts. Okay. Now we have the tap controller. Now this is your total instruction setup. Now a tap controller will be there which controls both the segments of your registry and the instruction decoder set. Okay. based on the instructions of either the mode select and the clock. Because this is tap, we are taking TMS, TCK. These are the TCK. These are the terms which we'll be using. Okay. So with the help of tap controller, the instructions will be given to both the instruction register, decoder set and the register set in order to perform the iterations of capture and updates. Okay. And parallelly, the tap controller will be issuing the this path of either choosing a normal operation or a testing operation. So this is your architecture. If you can understand this circuit, this is in an architecture form, we have put this. Whatever we have described here is same put in a format of architecture. Okay, now this boundary scan, what is the use of this boundary scan is whenever we want to have a normal operation, it should be in a position to just ship the data. If it is in a testing mode, it has to update this core logic responses, and that response has to be sent to the subsequent or successive boundary scanners that are placed in their path. Okay, so using this boundary scan, when there is a setup on your IC to have the self-test, one portion or one, on any IC if you take, there will be one provision of self-testing, the IC testing itself or a circuit testing itself whenever it is in use. Okay, so that we call it as built-in self-test. This short form you must be hearing frequently, BIST. BIST architectures or BIST controllers. Most prominently, this is the term that will be used by the maintenance engineers or design engineers also as well. Because design engineers, they need to provide this setup of the self-test on the chip itself. Okay, it's not every time we need an external setup for testing the circuit or testing the IC. So what is this built-in self-test is normally, maybe if you take this for testing a memory, say, as a simple example. Okay, this will be having a controller, what we call it as BIST controller, built-in self-test controller. Okay, this controller portion is that it needs to give the test vector or test sequence. Okay, it needs to give the test vector or test sequence to your core logic or circuit under test or core logic. And what it has to do in parallel is that it has to take the response of this circuit under test once the test vector is applied or the sequence is applied. Okay, now how do you say that a design is working properly, or how do you fix that there is no error? Is that whenever the truth values or truth table or fault free response, if it is known for us, fault free response, we try to take this response that is practically generated when you are giving an input will be compared with the fault free response. That means we try to compare these two. If both are similar, this is okay. testing is okay. That means your system is working properly. If the your fault-free response is different from the response that you have got while you are applying the test sequence or test vector, then it says that that particular combination or particular segment, your circuit failed. Okay, so that way the analysis will be done, or what you say, the testing of the um, total IC. Okay. Normally, yeah, when testing RAMs or ROMs, okay, the pattern or how the setup will be is something like in the RAM location, okay, like read data generation. You remember or you know how your RAMs or ROMs are operated? Like how does you get the information using a memory, whether it is a permanent memory or a volatile memory. You remember or you know a procedure? People are there?
I didn't remember, ma'am. Once, kindly please repeat.
Huh?
Didn't remember, ma'am.
I think it's better you people are called back to the campus. Huh? Out of 150 students, not even a single voice I can hear when I have a question. Hmm? Not even a single person. Just you log in and you leave. Log in and leave, that's all. Acha, anyhow, the video will be given. Why should we put the patients in hearing? Huh? Let us log in and do our own works. Not even a single question you will answer me. At least you come back to the original education system once you come to the campus. This is ridiculous. Just I'm telling something and you people are taking the recordings. It's your headache whether you read it or not. That is the later portion. Why should I take so much of pressure in giving you an added informations there? Huh? Okay, let it be. It's not my business. Okay. Like this built-in self-test, why we go for the BIST setup is that the more the number of transistors or the components that are getting integrated, the more the complexity of the designs are. And the more the complexity of the design, the denser will be the circuit board components. The denser the circuit board components, minute will be the paths for testing, and using the literal probes to test or tap the data becomes very impossible or difficult to tap the information at every segment on the board. So for this, what you say, highly integrated systems, okay, normally um, memory can be tested by writing what we call it as checkerboard pattern. Means that first we say if even odd sort of placing is there, say 0 1 2 3 4 5 6 and so on, if you are having. So first in even places it will be stored as 0, and at odd places it will be given as ones. Okay, and this forms one pattern. This will be applied to the board, or what you say, the memory element, and the response of that input applied will be taken and it will be again compared with the fault free line. The next step is that after taking the even odd as 0, 1, the interchange, make the even odd with 1, 0. Okay, this we call it as checkerboard pattern of testing the what you say RAM. Okay, and another test is that we have March test also. March. Okay, this March test is nothing but something like what you say, when you fix a value in one bit position. Okay, it's not that here we took even odd position. It can be any position. Okay, maybe if you are taking this any value, if you are taking, you apply this, get the response. Then what you have to do is interchange the bits. Now this becomes 1, 0, 0, 1, 0. That means two values you are able to get. So this is what we call it as March test. This is all like altering between 0, 1, 0, 1 you'll be taking. That is checkerboard, because checkerboard it is black white blocks, no? So the name has given as checkerboard. March test is that uh, some value what you have given will be complemented after testing. You get a new pattern. You shift the bit, you get then one more new pattern. So that's the way we try to give the inputs. Okay, when we are giving these inputs, or what is the setup, or what is the way these RAMs and ROMs are getting tested? Is that I said no, here the response is collected, and that response will be compared with fault free. So this we call it as monitoring segment. So this is what you say response generator. Response generator. Okay. So this both will be compared. Okay. And so what is that to be controlled is having a BIST controller, it issues the test pattern generator. That means what are the inputs that you have to give? Test pattern TPGs. The test pattern generator will get a controller signal to release the pattern, or what you say the test vector, to the circuit under test, or what you say the core logic. And the response of the system will be taken, and what you say this response will be compared. So this is the one what we have to do the comparison. So this test response will be monitored using a comparator sort of thing. And based on the outcome, your controller will be issuing the next set. Like say one pattern is given, its response is taken from the core logic output. This will be compared with your what you say the comparator response. If both are similar, next pattern will be released by the controller, or else your controller signals that there is an error. Okay, so for a self test, for a RAM in specific, say, what are the elements that a RAM can have is writing the data is possible, and reading the data is also possible. So that means read write data will be possible. Okay, for reading or writing, we need the address location, where to write or where from to read. But if you take ROM, will there be any element of or possibility of what you say data writing?
No, ma'am. It's a read
Uh,
only.
it's once stored, it will be read only. Okay, so it cannot have write. So this is read operation. Where from it will be reading will be decided by the address. Okay, this is the difference you have when you are testing the RAM and ROM. Okay, so if you are testing a RAM, okay, your BIST controller will be issuing what is the right data. What is the data that has to be written? The right data generation, okay, or generator to be specific. And what is the address in which it has to write the data? Okay, and the same BIST controller will issue, if it is testing, it will be something we said, na, this is given to your core logic. So if you have a core logic, you're testing, this will be given at the address location, the right data will be given, and this response, what is coming out, or what you say data output, should be compared now. With what it has to compare should be already stored somewhere else. So that address location of where the fault-free response is stored will be given as the read data generator. From that address, the information will be taken and this will be given to the response monitor, that is comparison. On comparison, the BIST controller will issue whether the circuit is working properly or not. It will signify that based on the output of the comparison. Okay, now this segment of comparing, or what you say, taking the response of the circuit and taking the, what you say, the fault-free response and comparing that, we call it as what is signature. Okay, the test circuit can be simplified by using the signature register. That means the signature means that it is the compressed data in the short string of bits. Compressed data in the short string of bits, we say. That is called signature. Okay. Now this signature will be compared with the fault-free, or what you say, correctly functioning circuit response. Or as simple as fault-free response will be compared with the signature of the CUT response. So the one or the component which generates the signature, the one which generates the signature, we call it as the multiple in signature register. This generates the signatures. Signatures is nothing but the compressed bits we are saying. Okay, string of bits. So this is multiple input signature register. That's why, because this is compression of bits, we are saying this is a set of many flip-flops. Okay. So what is the size, or what is the size of the vector, or what is the size of the signature decides how many registers you have in this MISR setup. Okay, MISR is nothing but multiple in signature registry, which is a combination or a setup of a few of the registers put together. Okay, so for ROM, there won't be further writing of data. This won't be there. This won't be there. Write data generator won't be there. And if I don't need a read data generation and comparison, this setup I can, what you say, simplify or cut down if I can replace that with the multiple in signature register. This multiple in signature register will have the combination of that fault-free response and the comparison operation both done together. Okay, so in place of this, in place of your read data generation and the what you say, the comparison setup, you replace that with MISR, multiple in signature register. Only the read data from the specified address location will be given to the circuit under test, and its response will be compared with the signature that is generated by the MISR, that is multiple in signature register. Okay, for your ROM, this also won't be there. This also won't be there. That write data generation won't be there. Directly, the address counter will give you what is the data that is to be given, and that will be compared here. Okay, so now this MISR, you have plenty number of multiple in signature registry formats. Okay, it is something like based on how many number of flip-flops we have in the circuit. It is decided by what we say, the vector size or test data size. Many textbook will be giving much more what you say, different terms for this. Okay, the size of this depends on how many number of bits you have in that signature. So something like here we need to generate the signatures, we are saying, and these signatures won't be following any specific format. Okay, normally if you take a registry setup, if you are taking, say, some 3-bit register, if you are taking, you are connecting one output to the other, and you are taking the outputs at this point, no? Normal D flip-flops, if you are taking D1, D2, D3 and so on. Now, what is the data you are giving in? Like based on that, either a sequential counter sort of thing, or sequential up increment format sort of thing, if you take, all combinations, it will be following either decreasing or increasing order of the, what you say, bits formation, either 0 to n minus 1 or n minus 1 to 0 format. Now, here, the format, or what you say, the pattern won't be in a fixed increasing or decreasing order. It will be something called as a random pattern. Random pattern will be coming out. Okay, and this pattern depends on how many number of bits you have. So actually, this will be called as a pseudo random, because why we call this as pseudo random is that based on how many number of flip flops we have, the randomness also varies. So something like pseudo random pattern generations we call it. So let me give this. Say if there is a 4-bit signature generator, if you want. Okay. Normally, this is made up of, or what you say, the structure is built up using a normal D flip-flop. So, say if I'm taking 4-bit signature, D1, D2, D3, D4. Okay. The output of the previous will be connected to next input. Okay, and there will be some feedback path which decides the pattern. Feedback path that decides the pattern. Okay, and how many number of bits or how many number of flip-flops you are using will be deciding what is the feedback path. per 4-bit, or what you say, this 4-register setup, the first output and the last output will be fed back. And this feedback element will be through an XOR operator, will be taken back into this input. That means we don't have any external input now. There won't be any external input. If you remember your structure of your SR or JK, we have the preset and clear. Only this preset and clear elements will be used either to store a 0 or 1 according to the first initial 0 or 1. Okay. And all these are in synchronous. Operation will be in synchronous. Okay, this is a system clock sort of thing. Now see here, what is the feedback element is your D1 will be Q1 XOR with Q4 for 4-bit. Now, how many number of bits we have? Say if you take it as n. If n is 4, this will be D1. Okay, let us see. Say if, oh, sorry. Now, if you see that 4 bits means 2 power 4, you need to get 16 combinations. Okay. Now use this clear or preset. Say I'm taking this order. Here Q1, Q2, Q3, and Q4. Okay. These are our outputs. Signatures, where from we are taking the output. Say at the first beginning, I make Q1 as 1, say, or let us take Q4 as 1. That means this one I make it as 1. How this is done? Sorry, how this can be done? Using this preset as 0. This is made 0 and clear is made as 0 or 1. No answer. Again, if you make all the clears to be 1 and independent presets as 1 except the last one, output of this will be 0, 0, 0, 1 now after clearing.
Yes, ma'am.
This is for first clock. Say for first clock. Now apply the clock. For the first clock, now this is 0. This is the initial pattern we are starting with. Now, what will be your Q1? Q1 will be this one. Na? Your updation of Q1 will be this D1. D1 is nothing but XOR operation of Q1 with Q4. So, the next value of Q1 will be 1. Because D1 will be Q1 XORed with Q4. 1 XORed with 0. 1 XORed with 0. This will be 1. So this Q1 goes here, Q2 goes here, and Q3 goes here. And next clock. This Q4 and Q1, if you XOR, because this is the previous value we are taking and we are updating that through D1. This is the equation I am following. Now, what is the new value of Q1? 1. This 1 comes here, 0, 0. This is the next signature. Third one. This is 1. 1 comes here, 1 comes here, 0. Likewise, if I go on writing the pattern, this is 1, 1, 1, 1. And here comes 0, 1, 1, 1. And now the next one is, it is something like with respect to clock. I'm not writing the clocks. So 1, 0, 1, 1. Next one, 0, 1, because these two are ones. XOR of these two ones is 0, 1, 0, 1. Okay. How many? Next, I'm writing here. 1, 0, 1, 0. This is Q1, Q2, Q3, Q4. Next one. 1, 1, 0, 1. 0, 1, 1, 0. 0, 0, 0, 0, 1, 1. Next, 1, 0, 0, 1. Next, 0, 1, 0, 0. Next, 0, this one, 0. Next, this 0, 1, 0. Next, 0, 0, 0, 1. Finished. We reached this. See, count how many number of signatures we were able to generate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And this is repeated. 15, na? Back, 15. Actually, this should be 16. What is the pattern that we are missing here? Which one we are missing? Which one we are missing? 2 power 4, 16 combinations should be there, but we are getting only 15.
All zeros, miss.
Zeros. All zeros are missing. All zeros are not happening. Okay. And if you check this, the patterns, what you are getting, the signatures, what you are getting, there is no specific order. Okay. That's why we call it as pseudo-random pattern. The signatures generated by are pseudo in nature, so pseudo random pattern, and the operation is something like based on the linear shifting taking the feedback. So this is named as linear feedback shift register. Linear feedback shift register. LFSR is one of the signature generating setup. One of the signature generating setup, a pseudo random pattern generating setup where all zeros won't be possible. But if we want all zeros to happen, what is that we need to do is when the moment it is going to the same repeated pattern, before it goes to this repeated or what you say initial pattern, what all the what you say the outputs that are zeros, that the q bars we try to take q bars, and this is one now. Before this is 0 0 1 0, that is outputs I am writing 0 0 1 0. Next it is going to the repeated signature. There what you have to do is take all the okay and try to make what you say the AND operation. Okay, AND operation, and make it as the feedback element. Oh, sorry. Connect that to feedback. Okay, and this clears. Or else one thing we can do. One more thing is before itself, if you want this to go to zeros, the pattern where from we want to take it as 0, because this becomes your what you say this is your 1. If you take the complement of this is 1 1 1. No? This is q bars we are taking. Q bars. Q bars. Now take these q bars through the AND gates, feed it back to your XOR. What happens? This is already 1. 0 1, already it will be 1. 0 1. 0 1, it will be 1. 1 over this becomes 1, no? All these are ones. This 1 will make another input of XOR to be 1 means that 1 over 1 is 0. This 0 will be shifted in. Now, if this 0 is shifted in, 0, 0, 0, this 1 discards and this 0 comes through. So, we need one extra setup of an AND gate, and the deciding inputs that are getting connected to the feedback, which will be making the system to generate all 0 signature also, or else it will be generating m minus 1 patterns that are possible, taking that normal shift operation. Okay, so now this is for 4-bit shift register sort of thing. Now, based on how many number of flip-flops you have, the feedback, this feedback, whatever we have taken, will be varying. Say if 4 registers or 6 registers or 7 registers are there, 4-bit, 6-bit or 7-bit shift register is used for generating the LFSR sequence. The feedback will be taken as the Q1 XORed with Qn. N happens to be either 4, 6 or 7. First output with the last output. Okay, 4, 6 or 7. If it is 5, second output will be XORed with 5th output. If it is 8, this is a prescribed feedback. Q2, Q3, Q4 XORed with Q8 will be done. If it is 12-bit shift register, 1, 4, 6, and 12 will be the feedback paths. If it is 14 or 16, the 14 or 16-bit register, Q3, Q4, Q5, Qn. That means n happens to be 14 or 16. If it is 24-bit shift register, Q1, Q2, Q7, Q24. Maximum 32-bit shift register is the maximum that any complex design can have. Even until 8 itself, it will be very difficult for a normal person. Okay, for an expert designer, they will handle these stages. For 32, Q1, Q2, Q22 XORed with Q32. So this is the feedback path. For only one thing, what we have seen is Q1 XORed with Q4 we have taken. This is tied to D1. It is your, the setup or the feedback parts defined for the number of flip-flops you are using for generating the sequences. Linear feedback shift register. Okay, so I'll stop here. Any doubts you have, get them clarified. Varun and Dheeraj, next Monday you'll be in the campus or online only? Next Monday, will that be offline or online?
People will be traveling mostly, ma'am. That week might be online.
Next week.
Yeah, personally, I'm traveling on Monday, so I don't know.
So 18th is the reporting day, final day
Oh,
of
yes,
reporting.
yes, ma'am. 18th is the last day. 19th, 20th are Saturday, Sunday, ma'am.
Okay, that means next week also it will be online.
Yes, ma'am.
Okay. Okay, like maybe after you come back as CRs, both of you check the classrooms whether the net and connectivities are there, the cabling is there properly and all.
Sure, ma'am. Sure, ma'am.
Okay, okay then. I'm stopping. No further doubts are there. I'm closing the session.
Ma'am, I have a
Like,
question.
Yeah. Tell.
Why did we choose these setup? Like, why does it have to be Q3, Q4? How is this decided?
Actually, this random signatures, like we said, na signature means compressed setup. Compressed setup. That means the string we are trying to compress, and automatically we are not giving any further input there. See, external input we are not giving. If you can see here in this circuit, where is the external input? We don't give any external input. Okay, this setup is that what is there fixed on a board or an IC. The moment you are switching on the IC, no manual what you say interference should be there. Automatically your circuit has to generate its own pattern, give that to the what you say the hardware there, get that response, and again compare what is that response that design is giving, and it has to validate itself whether it is working properly or not. Okay, so there won't be any external input. If there is no external input, say a normal shift register, if you take, what is the maximum possible, say, if I don't have this feedback, say, okay, if a normal 4-bit register is there, I'm taking, sorry, a normal 4-bit registry. What is that at the most I can give? Is this Q1 going to D2, Q2 going to D3, and Q3 going to D4. Okay. What I can get is these 4 outputs now. I'm not giving any input. I'm using this preset and clear to fix the values. Okay. First initial value. Now where from I'll get all the patterns. Say, if I fix this as say 0, 0, 0, 1, I don't have feedback. There is no feedback path. Like I apply the clock is common. For the next 4 clocks, what will be the inputs that can happen, or what will be the pattern I'll be getting? See here, if I make this Q4 1, I'll apply a clock. This Q1 gets to Q2. Okay, this gets to Q3, and this comes here. Then question is, what should be this one for the next clock? For the next clock, question comes, what should be this one and what should be this one? Only this gets shifted. This is for say clock 1 and clock 2. At the most, before you apply all the clocks, after 2-3 clocks itself, there is a question happening, what should be my input? Because I don't have any input here. Okay, so I take a feedback from the internal circuitry itself, fix the what you say the compression format. This is what we call it as compressing format. Okay, based on how many number of flip-flops we are having, we are tapping at different points. The tapping points will give you the all possible combination of the signatures. All possible combination of signatures. Your question can be best answered. Say, if you attempt to say for 8, you try for 8 and see if you are getting all possible, if you are getting all possible signatures. As we are saying this for 4, for 4 means 16, na? 16 combinations, out of that we are getting only 15. No all zeros. Okay, If
Yes,
I
ma'am.
take, if I take different tapping points, I'll be able to get the compressed format of all possible signatures, or all what you say, all possible combination of the patterns that can be happening for that many number of counters. Say if you take a counter of 4, increment counter or decrement counter, okay, we'll be getting right from 0, 1, 2 and so on to 15, no? Or else 15, 14 and so on to 0. But we are not using a counter here. We are using a shift registry aspect, compress the bit, or what you say, maybe rather telling this as compression, we can say that generate the pattern. Generate the pattern without feedback, only what few combinations you will get. We won't be able to get all combinations. Without feedback, the first input is missing. For every one shift, there will be 1 bit of data missing. For every one shift, you get 1 bit of data missing. No, 1 bit of data, this data will be missing.
Yes, ma'am. My
So,
question.
ah,
Yeah. So I know I was wondering. See, for n equals 32, you said Q1, Q2, Q22, and Q32. Is that the only combination that would
yes,
allow
yes.
all?
Because
Okay.
this is actually a big design segment we have, a chapter, but for your syllabus it is not there. It is based on the analysis of what tapping points will be giving us all possible combination of inputs.
Was
All
that
possible
decided with trial and error, or is there a logic to
no,
that?
no. This is predefined based on experimentations.
Okay.
The rule-based experiments are done, and the feedback paths are decided based on that experimentation. You cannot deviate the feedback things. Whatever is prescribed here, only that you have to take. You cannot deviate that feedback things.
Okay, ma'am. Thank you.
Yeah, further any queries?
So these are the most efficient tapping points, like for the table.
Not
Okay.
efficient, all possible combinations. Because taking 2 power 8 means you need to get all 2 power 8 combinations now. We don't have external input, and only taking the first and last feedback as we have taken here will not be able to give us all combinations. Only for this we were getting, but many flip-flops, if you have in the shift registry, more than one tapping point is needed. More than one tapping point will be needed.
Yes, ma'am. So for n is equals to 4, if we use Q2 and Q4, like Q2 XOR Q4, then we will not get all combinations, like all.
Patterns will be missed.
Oh, okay.
Yeah. Further, any questions further? Okay, someone is asking a doubt.
Ma'am, for the sequence 0, 0 and 1, we are getting missed 4 zeros, ma'am. For different sequences, we get different missed ones, ma'am.
No. I couldn't get your question. For
We are assuming here 0, 0 and 1, ma'am, as Qs. And we are missing 4 zeros.
0, 0. No. This pattern you are saying, this bits are
Yes, ma'am.
0, 0.
First, we assume 0, 0 and 1, ma'am. 3 zeros and 1. And we get missed 4 zeros. For different patterns, we get different missed
For
ones, ma'am.
any pattern you take. See, let me take say 0, 1, 0, 0. initial thing, initial. Okay, Q1, Q2, Q3, Q4 if you take. See here, 0, 0, 0, 1, 0. Okay, let me write all the combinations. We'll be getting the answer now. 0, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, and 0, 1, 1, 0, and 0, 0, 1, 1, and then next one, 1, 0, 0, 1, 0, you'll be getting 1, 0, 0. Finished. Where is that 0? Any assumed initial combination you take, the setup of, or what is it, the feedback of 1 and 4 we are giving now. That 1 and 4 is not able to define the all 0 combinations. Okay. Now, based on the initial pattern, or what you say, initial value you are defining, you need to introduce the feedback from the complement bit so that it will make the output go to 0, all zeros. In this where you can make it 0. See here. See here, this one. Here what you can do, after this, instead of making that going to what you say 1, 0, 0, if you take this as complement and tie it to the feedback, you get all zeros. Yes or no? You get all zeros. Then next iteration, you may fix that normal shifting. But all zero sequence won't be so important. It's not needed for testing many of the circuits. What we need is, except all zeros, other sequence is needed for testing. Usually, maximum number of circuits, we don't need that all zero. If it is needed specifically, we have to give a setup, something like this, take the feedback. What is the convenient way of taking is complement the value so that it defines this as 1. That 1 goes to the XOR operation, it makes that as 0. Okay. Clarify? Your doubt is clarified?
Yes, ma'am.
This path is, as I said here, this is not the only one tying we have. It depends on the pattern now. It depends on the pattern. Which one you want to make it as 0. Based on that, this feedback connectivities will be decided. Yeah. Hope I have cleared your doubt. Further, any queries, or else shall we stop?
No doubts, ma'am.
Any doubt? Okay. Okay, I'm stopping.